So, as Chaitanya sir said, today's this informative session will be delivered by my son Chinmay Bapat. He recently completed his master's in battery technology from Fraunhofer Research Institute. Earlier, he completed his BE Chemical from Pune University in 2015. Then for 3 to 4 years, he worked here for in chemical industry, and then he moved to Germany for his masters in October 2019. So there he, hello.
Please continue, sir.
So there he got an opportunity to make the thesis in battery technology. So this is the introduction for Chinmay. Further, he can take the session ahead.
Thank you, sir, for introduction of Chinmay. Today is the one of the best speaker, and his speech now will start to.
Yeah.
I request Mr. Chinmay Bapat to please take over the session and start delivering your very excellent messages. Please, sir. Chinmay sir, please.
Hello. Yes. Thank you so much, Baba and Chaitanya sir, for this introduction and this opportunity. I would like to thank Tech Forum and especially Vilas Rabde sir for this wonderful opportunity that I've got. And I'm still a beginner in this field, and I would just like to share the information which I have learned throughout the past 1.5 years. And I hope that you have an informative session. So as Baba mentioned, I completed my thesis at Fraunhofer Institute of Solar Energy Systems in Germany. And we are located in the city of Freiburg, that is at the southern part of Germany, near the Switzerland border. And it's a Sunday morning for me. It's 6 a.m. So I hope we have an informative session and we begin our Sunday morning with this information on battery chemistries for electric vehicles. For today's agenda, we'll first take a look at different types of batteries used in automotives and also in electric vehicles specifically. We'll take a look at some battery basics, which will help us understand the information which I'm sharing. Then I'll explain why lithium-ion batteries have been preferred and commercialized to such a large extent. Then we'll take a look at the actual lithium-ion battery chemistry with respect to anode, cathode, and electrolyte. I'll explain briefly about silicon anodes for lithium-ion batteries, which was the topic for my master's thesis research. And towards the end, we'll take a look at the prospective batteries for electric vehicles, battery chemistry specifically. And at the end, we'll conclude with a conclusion and outlook. So for the types of batteries used in automotives, all of us know the lead acid battery, which is used in classical internal combustion engines, but not so much in the electric vehicles. I'll explain the reasons why. We then have nickel cadmium batteries, which were initially tested for electric vehicles, but were not commercialized due to cadmium being toxic and the energy density being low. Then we have nickel metal hydride batteries, which are still being used in hybrid electric vehicles. Sodium nickel chloride batteries, which are high temperature batteries, which are used in some of the hybrid electric vehicles. And finally, lithium-ion batteries, which are used in the most of the electric vehicles today. So all these batteries work on the basic principle, that is during discharging, we have anodic oxidation, that is a species at the anode lose their electrons. And at the cathode, we have cathodic reduction, that is a species gain their electrons. So with respect to cathode, anode, and electrolyte, for the lead acid battery, we have lead oxide as the cathode and lead metal as the anode, with sulfuric acid as the electrode. For nickel cadmium battery, we have nickel oxyhydroxide as the cathode and cadmium metal as the anode. Cadmium is really toxic, so there have been some regulations and restrictions to the use of these batteries. And we have an alkaline electrolyte such as potassium hydroxide. For the nickel metal hydride battery, the cathode and the electrolyte stay the same, but the anode is an alloy of a hydrogen absorbing kind. For example, it is a combination of transition elements such as iron, nickel, cobalt, and rare earth elements such as lanthanum, cerium, etc. For sodium nickel chloride batteries, we have sodium metal as the metal casing and the cathode, and nickel metal as the anode. For the electrolyte, we have a combination of nickel and sodium conducting salts. And we have a ceramic sealing and a ceramic tube as a separator because of the high temperature of more than 300 degrees Celsius, that is operating temperature for these batteries. For lithium-ion batteries, we primarily have lithium cobalt oxide, which is the popular choice for the cathode material. and graphite as the anode material. The electrolyte is a lithium conducting salt, and lithium hexafluorophosphate is the most popular choice in this regard. Let us look at some basic battery parameters. Nominal capacity of a battery is nothing but the total ampere hours available from the 100% charge state to the 100% discharge state. Specific energy or gravimetric density is measured in watt-hour per kilogram, and it determines the battery weight required to achieve a given electrical range or a charge content. Specific power measured in watt per kilogram gives us the battery weight required to achieve a given performance target. Energy density measured in watt-hour per liter gives us the battery size to achieve a given electrical range. And power density measured in watt per liter gives us the battery size to achieve a given performance target. So energy is nothing but the total charge content of a battery, and power is the rate at which this charge is delivered to the outer circuit, that is at higher or lower currents. When we compare these battery chemistries with respect to the working temperature, specific energy, power, cycle life, and so on, we see that the lead acid batteries have a lower specific energy, a moderate specific power, a moderate cycle life, and a moderate efficiency, and a moderate self-discharge, due to which they were used in internal combustion engines, but not so much in the electric vehicles, since we need high specific energy and high specific power, and also a much larger cycle life for electric vehicles. Nickel-based batteries have a high specific power, good cycle life, but lower efficiency and higher self-discharge. That is, the energy content of the battery keeps on reducing even in idle conditions. Sodium-based batteries have a very high cycle life, high efficiency, and minimal self-discharge, but they also have moderate to low specific energy and power. Therefore, they were not used, or they are not used as much in electric vehicles. When we look at lithium-ion batteries, however, we see that they have favorable parameters or values with respect to all these parameters. And due to their rapid commercialization since 1990s, the cost of lithium-ion batteries has also reduced over the years. They're extremely cheap as compared to their cost in the past, let's say 10 years ago. So when we compare the applications of these batteries, lead-acid batteries are used in internal combustion engines, not so much in electric vehicles. Nickel-cadmium batteries, they are majorly used in portable electronics and emergency lighting. Nickel metal batteries are used in hybrid electric vehicles, and the most popular example from those is Toyota Prius. The sodium-based batteries are used in some hybrid electric vehicles previously, such as BMW AG, Mercedes-Benz Vivo, etc. Lithium-ion batteries, as we all know, are the primarily go-to batteries for all the battery-based electric vehicles, such as the Tesla models, the Tata Nexon EV, which is really popular in India in the past year, Mahindra XUV, and so on. When we take a look at the Ragon plot over here, we understand why this is the case. That is, lithium-ion batteries can offer or can be customized to deliver very high power or very high energy, which is higher than all these different kinds of battery chemistries that we saw. When we take a look at the different battery manufacturers for the popular car models in electric vehicles, we see that Samsung, LG Chem, Toshiba, Lithium Energy Japan, and Panasonic are some of the important and larger lithium-ion battery manufacturers. For anode, we see graphite is the popular choice due to its high electrochemical stability and efficiency. For the cathode, we have a mix of different cathode materials because each of them has their own pros and cons with respect to thermal stability, capacity, operating voltage window, and so on. Let us take a look at the working principle for a lithium-ion battery. First, let us look at the basic structure of a lithium-ion battery. On the anode side, we have a copper current collector, graphite as the anode, lithium hexafluorophosphate as the electrolyte, lithium cobalt oxide or any layered oxide as the cathode, and aluminum as the current collector on the cathode side. When we take a look at the working principle, during charging, the lithium ions are deintercalated or extracted from the cathode. The lithium ions move to the electrolyte and the electrons move to the outer circuit. The lithium ions flow to the electrolyte and meet with the electrons which are coming from the outer circuit, and they get intercalated into the graphite anode. And as you can see from this animation, an important observation which I find really interesting is that the graphite changes its color when being lithiated. Now, lithiation basically means the insertion of lithium molecules, and delithiation means the extraction of the lithium molecules. For the anode side, the materials which we have are carbon, lithium titanate, silicon, tin oxide. Out of these, graphite and lithium titanate have been commercialized, and silicon is a very hot topic at the moment in the past 10 years for research. For cathode, we have various lithium and transition metal-based compounds for the cathode side. And electrolyte, we have lithium hexafluorophosphate, which is the most popular and the only commercial electrolyte for lithium-ion battery due to its thermal and electrochemical stability, as well as a very wide working voltage window. But other materials are also being researched. Let us look at the high power versus high energy lithium-ion batteries. A high energy lithium-ion battery will have a better volumetric energy density at the expense of the ability to deliver a higher current. And a high power cell will have a low internal resistance and will be optimized to deliver current over energy density. For example, our mobile batteries are high energy cells since we want them to last longer, but they do not demand as much as power. As for example, power tools. In power tools, we have high power cells because we need high power, but for a short period of time. So the electrodes in the high power cell are thin and they have higher conductive carbon content to reduce the internal resistance. The current collectors are thicker and also coated to reduce the internal resistance. With respect to connections or the tabs on these batteries, they are thick and wide, and there are multiple tabs per electrode for high power cells. And in high energy cells, the electrode tabs are thin and narrow, and only one tab per electrode is sufficient. So overall, we can say that for high energy cells, they are optimized to deliver power at a lower rate for a longer time. And for high power cells, they are optimized to deliver power at higher currents with lower internal resistance. When we take a look at the different types of electric vehicles, that is from micro hybrid to full battery, I won't go into the details of this because I'm not an expert at this, but just as a general idea, the micro and mild hybrid need cells only for a short, batteries for a short period of time to deliver high power, whereas full battery-based electric vehicles are completely dependent on the battery, so they need higher specific energy. From this graphic, we can see lithium-ion batteries are suitable for all these needs because they can be customized to our application, whereas nickel metal hydride batteries are used mainly in hybrid electric vehicles. For the lithium-ion battery chemistry, let us take a look at the anode first. Graphite is the most popular choice, as I explained before, and it works on the principle of lithium intercalation. That is, the lithium molecules sit between the graphene layers of the graphite. Now, lithiation capacity means how much lithium molecules can graphite particles contain per gram. So graphite has a fairly moderate lithiation capacity of 372 milliampere per gram or ampere hour per kg. A lithiation potential between 0.07 to 0.23 volts versus lithium, and a minimal volume change upon lithium intercalation and deintercalation, that is expansion and contraction, is only around 10% when lithium ions are inserted and extracted back. Graphite has a very high cycling stability of more than 99% and high cycling stability and Coulombic efficiency of more than 99%. But the driving range of the electric vehicles today are limited by the moderate lithiation capacity of graphite. And therefore, it is an important need to improve the capacity of the anode in order to have a longer driving range per charge for electric vehicles. When we look at the comparison of the different anode materials, we see that the graphite has a moderate specific capacity. Lithium titanate has a low specific capacity, but a much better cycle life and stability. And therefore, it has been commercialized, but to a lower extent because of its low specific capacity. Tin oxides and tin composite oxides have very high specific capacities, but their stability and efficiencies are low, and therefore the cycle life is much lower, and therefore they're only in the research stage. Silicon, on the other hand, is a popular choice in the past 10 or 15 years to succeed graphite or combine with graphite to give us longer range EVs due to its extremely high specific capacity of 3578 ampere hour per kg, which is 10 times that of graphite. Silicon alone has a lower conductivity and poor structural stability as compared to graphite, Therefore, at the moment, silicon is being combined with some sort of carbon in the form of graphite or other forms of carbon, so that we form silicon carbon composites, which can have a capacity of around 1000 to 1500 ampere hour per kg and more than 300 cycles. And they are still in the research stage. When we take a look at the lithium-ion battery cathodes, we primarily have three kinds of structures, as we see in this graphic. That is layered oxides, spinel lattices, and olivine or polyanion oxides. Layered oxides offer two-dimensional mobility of the lithium ions. Spinel lattices offer three-dimensional mobility, and olivine or polyanion oxides offer only linear mobility. Layered oxides, they are typically known as nickel, cobalt, manganese or NCM cathodes, and they are very popular due to their high theoretical and practical capacities, and they make an ideal counter electrode for graphite. The largest drawback, however, with this is their safety and cost due to the use of cobalt. When we include manganese and aluminum in their chemistries, they have a slightly improved safety, but the risk is not fully gone because cobalt is still there. When it comes to spinels, lithium manganese oxide are cost effective and safe with a potential of 4 volts versus lithium. However, they have the lowest specific capacity amongst these three materials, and that they are limited in their longevity due to the dissolution of manganese into the electrolyte when the battery cycles. For olivines, they offer a stable chemistry with higher capacity than spinels, but they are limited due to their low potentials of 3.5 volts with respect to lithium. However, recent developments have incorporated nickel into the olivine structure, and it has led to an increasing potential of around 5.2 volts, which is better for the battery operation. When we take a look at the comparison of lithium-ion battery cathodes, we see that the cell voltage varies between 3.2 to 4.7 or 5.2 volts, as I mentioned before. And the practical specific capacity lies in between 120 to 190 ampere hour per kg. So if you take a look, if you remember, the capacity of graphite was around 370 and the capacity of silicon was around more than 3000 theoretically. But the capacity of cathodes is much, much lower. And that is why I mentioned that to improve the EV driving range, we need to have higher capacity anodes, because in the cathodes, the capacity cannot be increased to a larger extent due to their structure. And therefore, cathodes determine the cell cycling stability and operating working voltage window. When it comes to the use of these particular transition elements with respect to these particular parameters, we see that nickel lies in the middle for all these parameters, and cobalt and manganese lie on the opposite ends. Since cobalt is expensive and toxic, more recently increasing nickel content and eliminating cobalt content is becoming prominent. However, there are three major problems when it comes to increasing nickel content. That is cyclic instability, thermal instability, and the instability or sensitivity when it comes in contact with air. High nickel-based cathodes also suffer from cracks during charging and discharging, and it exaggerates the surface reactivity, due to which there is a higher chance of metal dissolution into the electrolyte and rapid capacity fade as the cycling progresses. Therefore, it is important to optimize the manganese and nickel content while still keeping some sort of cobalt content to keep the cell stable. Now, let us look at the different lithium-ion battery electrolyte. Let's take a look at the prominent lithium-ion battery electrolyte. That is the lithium hexafluorophosphate salt, which is dissolved in organic solvents such as ethylene carbonate and ethyl methyl carbonate. This lithium hexafluorophosphate, that is LiPF6, fully dissolves and dissociates into anions and cations in a proper solvent. It gives a high ionic conductivity, high thermal and electrochemical stability. It provides for a stable SEI formation. SEI is basically a solid electrolyte interface layer that is formed at the anode. It is formed when the electrolyte decomposes and deposits on the graphite anode in the form of a passive layer. Now, this layer has to be passive. Otherwise, more and more electrolyte will get decomposed and deposited onto the electrolyte, and we'll have a loss of usable lithium ions. So this lithium hexafluorophosphate dissolved in this particular solvents offers stable SEI formation and cycling stability. It also offers good wettability of electrolytes. That is, the electrolyte can penetrate through the electrode better. A safety concern is that this particular electrolyte is flammable and moisture sensitive, so we have to be careful with it. As I mentioned, it is dissolved in ethylene carbonate and ethyl methyl carbonate to increase its ionic conductivity, decrease the viscosity, increase the penetration and wettability. Additives such as fluoroethylene carbonate and vinylene carbonate are added to improve the cell stability, prevent gas evolution, and prevent formation of hazardous substances such as lithium fluoride during the cell cycle. Now, this particular electrolyte has been commercialized to a higher extent because it offers all these advantages, and the operating working voltage window is also suitable for the anodes and cathodes that are being used. So different electrolytes need to be researched and commercialized in order to have a suitable competitor. Let us move on to silicon as a lithium-ion battery anode. Silicon has a theoretically high lithiation capacity of 3572 milliampere hour per gram or ampere hour per kg. This is 10 times that of graphite theoretically. It is naturally abundant in the Earth's crust and non-toxic in its natural forms. It has a mature processing technology due to its application in semiconductor manufacturing, as we all know in the past decades. Here we see a crystalline silicon lattice. Upon lithium insertion, the lithium and silicon alloys together, and we have a lithium silicon alloy as the intermediate stage. During lithium extraction, the crystal structure gets disintegrated and we have the formation of amorphous silicon. This particular alloying property or the alloying reaction is different from the graphite intercalation that we saw before. And this is the reason why the specific capacity of silicon is that much higher than graphite. But this particular alloying reaction and the increasing volume is the first challenge for silicon-based anodes. That is its enormous volume change upon lithiation and delithiation. So when these particles continuously expand and contract, they do not retain their structures as we saw. And therefore, the solid electrolyte interface layer, which I mentioned in my previous slides, it gets broken up and reformed, and gradually it becomes thicker and thicker, as we see in this particular graphic. And as it becomes thicker and thicker, lithium ions, which shuttle between the electrodes, are stuck in the SCI layer or at the electrode. And therefore, we have lower cycling stability due to these internal chemical reactions, and also irreversible lithium trapping at this particular electrode. Silicon, as I mentioned, has a lower conductivity individually as compared to graphite, and therefore we need to add conductive additives in the anode active material as well as in the electrolyte to improve the conductivity. Material degradation due to the silicon expansion and contraction lead to decreasing cell capacity from granular to cellular level in various phenomena such as grain detachment, internal fracturing of the silicon particles, coating expansion and delamination of the anode active material from the current collector itself, swelling and distortion at the cell level, and also rapid electrolyte consumption and gas production due to the continuous SCI breaking up and reformation. As we increase the silicon content in the anode, the capacity degradation also accelerates. So what is the solution to this? Because we want to use silicon, but it has these problems. One of the research approaches is to encapsulate or cover these silicon particles with a conductive carbon shell to accommodate the volume expansion, prevent the material degradation, and improve the conductivity. And that is the formation of silicon carbon composites. This was the topic of my research, but I'm not allowed to share any information about my research. But what I can say is that it is a very promising avenue, because silicon can give all these advantages with respect to increasing capacity, and it can improve our driving range as well. And fast charging is possible because the alloying reactions with silicon are much faster than the graphite intercalation and deintercalation. The main challenges, as I mentioned, are the volumetric changes and the cycling stability. So as the midterm goal, silicon carbon composites can be a solution. And as a long-term goal, pure silicon anodes could be a solution if we develop good conductive additives and good working electrolytes with it. Let us have a look at some future low-cost batteries which we could see being commercialized in the near future. Sodium-ion batteries were developed together with lithium-ion batteries in the 1980s. However, their inferior performance relative to lithium-ion batteries was the main reason for their fade. However, the recent upsurge in electric vehicles and energy storage using lithium-ion batteries could cause a shortage of lithium in the near future, and therefore sodium-ion batteries have been dealt with great attention and research again in the past decade. Since 2010, the slogan of "Beyond Lithium" is trending, and therefore research in sodium-ion batteries has been intensively focused to develop better electrode materials and develop better sodium-ion batteries altogether and see whether they can be commercialized. And most important factor in this is that our table salt, which we use every day, can be used as the electrolyte conducting salt to use to shuttle the sodium ions. So sodium ion batteries work or have the similar reactions to lithium ion batteries, only difference being the sodium ions shuttle between the two electrodes. For anodes, we have hard carbons, that is disordered carbons, which is opposite of ordered graphite carbons, or sodium titanate, tin antimony composites as the anode. For the cathode, we have similar structures as we saw before in the form of layered sulfides, fluorides, sodium transition metal phosphates, or sodium transition metal oxides. Electrolyte choices are sodium hexafluorophosphate or sodium perchlorate dissolved in a suitable solvent such as propylene carbonate. Can sodium-ion batteries be an alternative to lithium-ion batteries? Well, I think yes, only if these challenges are resolved. First and foremost, sodium cations have a larger cation radius than that of lithium, and therefore the expansion and contraction that we saw before when due to lithium intercalation can be exaggerated when we use sodium, which can disrupt the structural stability of the intercalation compound. So that challenge has to be solved. Sodium alone as a metal has a lower gravimetric capacity as compared to lithium. Therefore, sodium-ion batteries will have lower energy densities than the corresponding lithium-ion battery. Therefore, we'll need more number of cells in a battery pack. Sodium transition materials, or that is the cathode materials, are highly hygroscopic, that is water sensitive, and therefore they require meticulous handling. As I mentioned, that there was a lack of research on a full-scale level in the previous decades due to the focus on the lithium-ion batteries. So that is improving slowly in the past decade. And the main reason for that is the low cost of metal ores to extract and process sodium, because we use our sodium chloride salt every day. Also, a few companies in the past decade or in the past few years are promoting various prototypes of sodium-ion batteries for commercialization. Towards the end, we have metal air batteries, which have a higher energy density as compared to lithium-ion batteries due to the use of transition metals such as aluminium, zinc, etc. For the reactions, we have cathodic oxidation reduction at the cathode and anodic metal dissolution at the anode. That is, the metals get oxidized and they form metal oxides. And these metal oxides lead to the exhaustion of the metal anode. So when the metal anode gets exhausted in the form of metal oxides, we can simply remove the anode and replace it with a fresh metal, and we can run our cell again. However, research is also being focused on making these reactions reversible so that we can either have a battery chemistry similar to sodium-ion batteries, or we can take out this exhausted metal oxides and extract pure metals from it and recycle them. So for the anodes, we have alkali metals and alkaline earth metals such as potassium, lithium, sodium, etc. And also first row transition metals such as iron, zinc, aluminium, etc. For the cathodes, we have basically a catalytic gas diffusion membrane, which basically filters out the oxygen from the surrounding air, and this oxygen can then react with the metals as we see in the reactions. For the electrolyte, we have two types of batteries, that is aqueous and non-aqueous batteries. As the electrolyte, we have potassium hydroxide for aqueous batteries, and for non-aqueous batteries, we have ethers. This particular graphic just shows the amount of research that is being done on these particular metals. I would also like to mention here that an Israeli company known as Phinergy, P-H-I-N-E-R-G-Y, Phinergy, and also our own Indian Oil Corporation are working towards recyclable aluminum air batteries for electric vehicles in India. And in the last year, we have a lot of videos on YouTube and other research community channels on aluminum air batteries, which could be commercialized soon. Towards the conclusion and the outlook, I would like to state that battery chemistries are highly directed by their technological demands and environmental impact. Lithium-ion batteries have dominated the commercial market in a variety of applications since 1990s. Silicon carbon composites could be a midterm solution to improve the EV ranges and fast charging capabilities. Better electrolytes and conductive additives could push the envelope towards pure silicon anodes in the future. The main problems with lithium-ion batteries and the main challenges right now is the battery recycling, lithium and silicon mining, which is really hazardous for the environment. Compatible electrolytes for lithium iron phosphate cathodes, and intensive research in order to concretize the sodium ion battery and metal air battery chemistries are the focus area in research today. For electric vehicles, as far as I think, lithium-ion batteries will continue to be the state of the art for the next decade at least, until a competing technology like a sodium-ion battery or a metal air battery can reach the commercial stage from research. And that was my presentation. And I thank you for your attention. And I'm welcome to any questions or feedback that you may have.
Thank you, Chinmay Bapatji, for wonderful presentations on lithium-ion batteries and other batteries also, other technologies also. You already explained some of the insights of activities, processes through excellent graphics, as well as in a very simple wording. So now I request all participants to open up their audio to their mute and start asking. I request everyone to introduce before asking the question and then ask the questions. So, question and answer session is open now. There is a one question asked by in the chat box.
Yes, I cannot see the chat box, sir, at the moment. So could you please read out to me? Or
Okay.
see if I can switch to Zoom.
Mr. Ramesh Telang, he is asking something about lead acid battery review. Required. Are you there, Mr. Telang, sir?
Yes.
Please introduce yourself and ask the question.
I am muted. We manufacture in our company a small polypropylene fibers, which is used as a binder for the lead acid, the masala which is being pasted into the grid of the for construction purpose. It's a binder. So do you require any binder for
Yes, sorry.
Please continue, sir. I have muted someone else who is in between. Please continue, sir. Telang, sir, please continue.
Do you require a polypropylene fine denier fiber without which the present lead acid batteries cannot be made, because it acts like a binder for the masala, they call it. Which is
that's true. That's true. In batteries, we have binders, and also as far as lithium-ion batteries, I know that we also use binders because due to the continuous lithium insertion and removal, the active material gets disintegrated and it can lose electrical contact with the current collector, and therefore binders are also necessary in lithium-ion batteries as well. And I think also you mentioned in lead acid batteries, they might also be needed.
Lead acid batteries we are regularly supplying to Excite for last about 20 years, all over India. So
that's really good to know, sir. That's really good to know. Yes.
So whether it has any relevance in the case of these new generation batteries, I wanted to know.
Yes. So particularly, which binders did you mention? Polypropylene.
Polypropylene, because that's the inert.
In lithium-ion batteries, polypropylene is used as a separator to separate the anode and cathode who have electrical isolation. Okay. But in the binders, one example is a PVDF binder, that is polyvinylidene difluoride, and other binders such as carboxymethyl cellulose, etc., are being used.
They are not in the fiber form. They are in the liquid form, I suppose.
Exactly. Yes, they are in the liquid form.
Okay.
They're either dissolved in organic solvents or water.
So PP cannot be dissolved. It's a inert material.
Yes, yes. Then therefore polypropylene or polyethylene are used as separators in lithium-ion batteries at least.
Okay, I understood.
Yes.
No more questions from my side.
Thank you, sir.
Thank you, sir. Thank you, sir. Mr. Gunesh Talu is there. Let me introduce him. He is our last speaker, which has on not EV, other auto industries research. He has presented himself to the industry. It was a wonderful presentations made by him. And if Mr. Talu is there, Gunesh Talu is there, if you can introduce yourself and ask any or give a comments on this. Mr. Talu, Mr. Gunesh. Okay, let me ask one more question from my side. I'm Anil Chaitanya, founder member of this Tech Forum, and work in IT industry. I run my IT industry. My question is, there are various applications other than EV or auto industry. Are you come across with other industrial applications used by this type of batteries, or are you under process of developing technology or any specific research for other industrial applications than auto?
Right now, sir, lithium-ion batteries that we are developing are mainly focused to electric vehicles. But an important aspect, as I mentioned, with high energy or high power cells, is that the high power cells and high energy cells are both required in lithium-ion batteries in terms of electric vehicles. And when we optimize any battery for the automotive sector or the power tool sector, then we can use these particular batteries in any other form, because we use our lithium-ion batteries, our button cells, in our portable gadgets or electronics. We use the lithium-ion batteries in mobile devices. So various other applications. So if we optimize any battery chemistry to deliver either a high power or a high energy, then based on our application, we can use these batteries for any application that we wish to use.
Okay, wonderful, wonderful. Because there are many, Tech Forum has a many other type of industries member, and some of them in various industries, they need type of energy sources to be used, updated energy sources. So
yes, that is true.
If you are interested, or if there any research on this being going on, Tech Forum can organize a meeting with them, so they can share requirement and technology to each other.
Definitely, I would love to do that in the future once we have some development and once we can reach at least at the pilot plant scale. Then I would definitely like to meet with these people and understand their requirements, so we can focus our research in that particular application at least.
Yes, yes. Who's there? Raise the hand. Mr. Shashank, please, please introduce yourself and ask the question.
Thank you, sir, for giving me the chance. I, Professor Shashank Gowde, working as an EV program coordinator in MIT ADT University. I firstly thanks Bapat sir for a wonderful insights regarding the lithium-ion battery, which are the current trend, and the upcoming batteries regarding the sodium-ion batteries. Now, one of the question is that when we are going to say the lithium-ion battery, SCI layer formation, dendrite formation is one of the challenge. So, can I have your insights about the SCI layer or dendrite formation on the 6 types of cathode, where it will be on the higher side and where it will be on the lower side?
Yes, sir. That is a really excellent question, and I think you really have some really good insights. So lithium dendrite formation occurs at the anode when the potential of the anode material is towards zero, and at the cathode when the potential is on the higher side. So when we, as I said here, the normal working potential for the cathode is around 4 volts, which is suitable for the current electrolyte that is being used, that is LiPF6. If you increase the potential further towards 5, then we have a chance of electrolyte decomposition on the cathode, and similar to SCI on the anode, we have a CEI, that is cathode electrolyte interface on the cathode. So it's got to do with the potentials, that is the oxidation or reduction potentials at the either of the electrodes. And with the SAI formation, the chemistry of the anode and the cathode, that is the structure, is also important, as I explained with graphite or silicon. And it is a similar case with the cathodes. That is, if the lithium or any ions which are being shuttled, if they are not, if they do not come out after they go in, then the lithium concentration slowly gets saturated, and then we have lithium plating on either of the electrodes. So we need to optimize the working voltage, the electrolyte, and the electrode structure.
Thank you, sir, for explaining.
Thank you, sir.
Yes, I hope that was that answered your question.
Yeah, sir. One more question, can I?
Yes.
Yeah, please ask.
In case of sodium ion batteries, while your presentation, you are showing the disadvantages or the limitations.
Yes.
So in that, I have to ask about the structural changes. What is the percentage of the structure, more percentage of the structural changes which are going to be occur in the sodium than the lithium ion? Because okay.
Yeah. I understood your question. So when you talk about graphite and lithium, the structural changes were around 10%, because the cation radius of lithium is 0.76 angstrom, and it is around 30% more for sodium. So we can expect around 20 to 30% structural changes if we continue to use graphite. But if we use any other material which can reversibly integrate at the anode, as I mentioned, hard carbons, because we cannot use graphite because the spaces in between the graphene layers are not sufficient to intercalate the sodium. So when we use these particular anodes, the volumetric changes are slightly higher than lithium. I do not know the exact percentage, but my guess would be around 20% at least.
I would like to tell one more thing here. There are a couple of our members, few of our members, who is also doing research on such type of area. So we will introduce him to you, and you can share your questions and information to each other.
That would be really nice, sir.
I request all of you to become a Tech Forum member. That will help us to be keep connecting each other very fluently and easily. Otherwise, after the session, we lost connections, and at the time when there is an opportunity to be get connected, we are not able to stressable to each other. So I request all of you to become a member of a Tech Forum. You can contact me or Vilas Rabdeji. In this case, take my number 9822557463. I will repeat again, 9822557463, and send me the message. I are interested in Tech Forum. I will contact you back. Okay, let's move to next question. Mr. Pramod Ubare, you have raised your hand.
Yes.
If you are there, please introduce yourself and ask the question.
Hello. Thank you for this opportunity to ask the question. I am Pramod Ubare. I am working as a model bus developer at American Axle company. I'm mainly focused on to the motor control side and efficiency improvement algorithms. But as I keenly interested also into the battery technology, I'm not so much deeper into that, but I'm just at the modeling level only. And thank you, Chinmay, for following this research with us, and we are so thankful for that. There are two questions I have now. First question is about, like, if you select a lithium ion into the high power region, then is there any specific disadvantages lies along with it, and or any temperature issues are we need to take care, or any disadvantages you can just comment on it. And another second question is, like, there is another competitor for the lithium ion is a fuel cell. So can you just please comment the comparison of this one, and what is your thought on that, like in future, or what is insight into this comparison of these two? So thanks.
Yes, I understood your first question. Could you please repeat the second question? There was some disturbance.
There is another competitor for the lithium ion is a fuel cell. So the chances of fuel cell and lithium ion, how they will compete each other in case of electric vehicles. and what are the scope of these two technologies in future?
Okay, yes, understood. Thank you for these interesting questions. With respect to high power cells, I would like to state that since we need a very high amount of output in the form of higher currents, there is a chance, or there is certainly actually what's happening is that the temperature of these batteries internally is towards on the higher side. And as we know, and we have seen so many news articles that the lithium-ion batteries are exploded either in the mobiles or in some other cases. And that is because of the thermal runaway. That when the temperature increases in the lithium-ion battery, then the side reactions in the batteries on the electrode side, they get increased. And this is an unending cycle. Because the higher temperature, the side reactions increase, and because the side reaction, the temperature keeps on increasing. So it is very important. And today, the battery management system are an integral part of any lithium-ion battery pack. That is, they continuously monitor the temperature and they continuously make sure that the temperature does not go beyond the particular set level. And if it goes, then it immediately shuts off the power and shuts off any chemical reactions happening. So with respect to high power cells, we have to pay attention towards the temperature of the battery, and the internal resistance is very, very low. That is, we need the lower resistance, but it always, as the cells keeps on cycling and delivering power, the temperature will surely increase. And with respect to fuel cell technology, first of all, I will have to say that I'm not really into the fuel cell technology, but what I know from my limited research is that there is hydrogen storage is an important aspect in at least some of the fuel cells, and which is still a topic of research being today. We have some hydrogen cars in Europe and America, which have been started recently. And the fuel cell technology, it has a very bright prospect. And I think, as I mentioned, for lithium-ion batteries, we need some other competitors. And I think fuel cells could be a very good competitor, along with hydrogen-based cars, which use hydrogen as a fuel instead of batteries. So I think these two could be competing technologies in the near future.
Okay. On first question, I want little more clarity. Like we need to take care about the temperature. Yes, for the high power, only deal with it. But is there any special like for engines or motors, will have thermal jackets who do the temperature management into this one. Just like we also have the battery management system also. But do we require any special thermal compensation, or just like to compensate that temperature? Any special system like oil thermal, what we call it, just cooling system? Yes, thermal cooling system.
We definitely have cooling systems and coolants also for lithium-ion battery packs, and they are manufactured by different companies. And one of the popular companies is Henkel, which manufactures the adhesives, which also allow for thermal heat dissipation, and also they manufacture coolants. And there are many other companies that when a battery pack is being manufactured, many lithium-ion batteries are packed into modules, and these modules are made into packs. And in between these individual modules, we have this cooling system, which reduces the temperature, and also the adhesives, which help to seal the batteries, but also help to dissipate the heat. And there are also certain coatings, thermal conductive coatings, which help to dissipate the heat out.
Okay. So then those thermal coolants are there. Those thermal coolants will be normally the oil cooled, water cooled, or any special coolants material are different than like this.
Water is a coolant, but it is used in the form of channels. And there are other coolants which are specific organic compounds, like we have organic compounds in adhesives or in some other conductive coatings. There are also some organic compounds which are used as a coolants, which can flow or in the form of solid, or let's say solid like pastes or gel form, which are also used.
Okay. Thank you. Thank you, sir.
Thank you.
Thank you for
Hello. Hello. I cannot hear us. Chaitanya sir, you are muted, I think.
Oh, I'm sorry. Okay, let us take one more last question. if there anyone is interested, because we are all almost at closer to the program timing, program schedules. Is Mr. Rabde is there? Do you have any comments, sir?
Yes, yes, I am very much there.
Your audio is not clear.
No, I am very much there. I have a sore throat.
Oh, okay. Please take care of your health. Okay. Considering
It was a wonderful session, I must say.
Thank you, sir. Thank you for this opportunity, and it was really great to interact with all of you esteemed members. And this is a great opportunity for me. Thank you so much once again.
okay, friends, let us conclude the session today. First of all, thanks Chinmay Bapat for giving wonderful insights of your research, which is required for today's industry as well as technology. Uh, I would like to take a chance to tell one interesting thing here. The Tech Forum is the platform who want to represent his research to the industry, who want to interact with his research to the industry. We are the platform, and Chinmay Bapat is one of the best example here. There are many technologies also available in various areas. You all can come and explain your technologies to industry here on this Tech Forum platform. We love to do such type of activities for us. We have done many activities, also schedules for the many activities. So let me once again thanks to Mr. Bapat for unfolding excellent insights of lithium-ion battery. As well, thank you for Mr. Bapat, his father, for introduction of Chinmay. And thank you for all participants who has joined today. We really respect your knowledge, your contribution to the industry, and your really busy schedule in the industry. Still, you join here as a Tech Forum session and participated today's session. So once again, I have thanks to everyone. Thanks to Vilas Rabde for finding out excellent speakers like Mr. Bapat. And I give a thanks for everyone once again and declare as a session is over. Thank you, sir. Thank you.
Yeah, thanks
Thank
a
you
lot
so
to
much.
giving opportunity to Chinmay to share his knowledge. Thanks.